Assalamualaikum. My name is Cik Haikal. Today I want to compare Ferris wheel and clock. So, first of all, I want to go for introduction first. Geometry is a originated from the Greek word yet is a geo and metron. Its origin date back to ancient civilizations such as Egypt and Mesopotamia, where it was used for land measurement, construction, and astronomy. Geometry later developed into a formal branch of mathematics in ancient Greece, especially through the work of Euclid, whose idea laid off the foundation for geometry and continue influencing modern mathematics today.
Hi, my name is Dinesh Ashraf, and today I'm gonna talk about Case 1, a wall clock on slide 9, a timeless masterpiece designed to measure intervals of time. Before we go into the wall clock, let's talk about the origin first. So, origin of the wall clock. The idea of keeping track of time has existed for thousands of years. Long before wall clocks appeared, ancient civilizations like the Egyptians used sundials and water clocks to measure time through the movement of shadows of flowing water. Mechanical clocks start to appear in Europe in the 14th century, often as large structures in church towers that rang bells to signal the hours. These early clocks did not even have faces because telling the exact time was less important than marking significant moments of the day. By the 17th century, clocks became smaller and more precise. The invention of the pendulum clock by Christian Huygens allowed for greater accuracy. Eventually, wall clocks became a common feature in homes, and the 20th century introduced quartz movement, making clocks highly precise, affordable, and widely accessible in households around the world. After talking about the origin of a wall clock, let's dive deeper about what is a wall clock. A wall clock is a fascinating combination of mathematics, design, and timekeeping. Most clocks' faces are circular and symbolizing the endless flow of time and providing a smooth surface for the hands to rotate. The hour, minute, and second hands are straight lines radiating from the center, constantly forming angles that change every second, minute, and hour. These angles can be even calculated using simple geometry, a classic problem in mathematics. Triangles often appear in the design of the hands or arrow tips, adding visual style while pointing precisely to the hours. In some clocks, numbers are arranged along the circumference in a perfect radial pattern, creating symmetry that makes the face easy to read from any direction. Modern wall clocks can take square, rectangle, or even polygonal shapes, showing that geometry is not just functional but also artistic. The ticking sound comes from the escapement mechanism, a clever arrangement of gears that divides time into equal intervals. Some clocks have multiple faces showing in different time zones, combining geometry, movement, and global perspective in one elegant object. After knowing what is a wall clock, let's talk about the problem that exists to this wall clock. A mechanical wall clock has a diameter of 24 cm. The minute hand is 10 cm long. Using geometry, we will explore the following question using pi equal 3.142. The first question is, what is the total area of the circular clock, representing the space it occupies on a wall? Second question is, what is the exact interior angle between the hour and the minutes hands when the time shows 3:40? And the third question is, what is the length of the arc traveled by the tip of the minute hand over a duration of 20 minutes? Now let's talk about the solution of the first problem. What is the total area of the circular clock representing the space it occupies on a wall? So given that diameter is 24 cm and radius is a diameter divided by 2, so we know the radius of the circular clock is 12 cm. So let's use formula area A equal to pi r square. So 3.142 times by 12 square equal to 452.448 cm square. So that is the total area of the circular clock, diameter 24 cm. So the second question, what is the exact interior angle between the hour and minutes hands when the time shows 3:40? So step 1, we need to know what is the minute hand position. So total interior angle 360 degree divided by 60 minutes, we will get 6 degree per minute. At 40 minutes, needs to times 6 to get 240 degree. So next we need to know the hour hand moves. 360 degree divided by 12 hours, we're gonna get 30 degree per hour. So divide 30 degree for another 60 minutes to get 0.5 degree per minute. So when we look at the question asks is between the hour and minutes hands when the time shows 3:40. At 3:40, we need to use the information that we already get, 3 hours times 30 degree plus 40 minutes times 0.5 degree. So we're gonna get 90 plus 20 equal to 110 degree. Step 3, finding interior angle using difference. So theta equals 240 minus 110, and we're gonna get 130 degree. So that is the answer. For the third question, what is the length of the arc traveled by the tip of the minute hand over a duration of 20 minutes? Step 1, we need to know the identified given data. Radius, the length of a minute hand equal to 10 cm. Time 20 minutes, so that means 20 over 60. Simplify 1/3 of the circle. After that, step 2, find the central angle theta. Theta equal to 1/3 of the circles times 660 degree, we will get 120 degree. Step 3, convert degree to radian. 120 times pi over 180, we're gonna get 2 pi over 3 radian. Step 4, finding arc length. S equal r theta. S equal r theta means 10 cm times 2 pi over 3 radian, we're gonna get 20.94 cm. So that is the length of the arc traveled by the tip of the minute hand over a duration of 20 minutes.
So for our second case, we chose the London Eye. The London Eye was designed to provide aerial views of the city for tourism and observation. The London Eye originated as a project to celebrate the new millennium and was created to showcase modern British engineering and design. It was designed by architects David Marks and Julia Barfield after winning a design competition with the aim of building a landmark that will represent London in the 21st century. Construction began in the late 1990s, involving advanced engineering techniques to assemble the large circular structure safely along the River Thames. The London Eye officially opened to the public in 2000, quickly becoming one of the most popular tourist attractions in the United Kingdom. Although it was originally intended to be a temporary structure, the overwhelming public response and success of the attraction led to it becoming a permanent landmark. Today, the London Eye is not only a symbol of modern London, but also an excellent example of how geometry and engineering work together to create a stable, functional, and visually impressive structure. The London Eye is a giant observation wheel standing 135 meters tall, with 32 glass capsules, each capable of holding up to 25 passengers. A full rotation takes approximately 30 minutes, allowing visitors to enjoy breathtaking panoramic views of London, including famous landmarks such as Big Ben, the Houses of Parliament, and St. Paul's Cathedral. The structure is constructed mainly from steel and is supported by triangular trusses and tensioned cables, which distribute the weight evenly and provide stability, ensuring that the wheel remains safe and balanced during operation. From a geometry perspective, the London Eye is a perfect circle. While each capsule is shaped like a cylinder, the spokes radiate out from the center of the wheel at equal angles, creating a symmetrical pattern that helps maintain balance and structural strength. This careful use of geometry allows engineers to calculate distances, angles, and loads accurately, making the wheel both functional and visually harmonious. Interestingly, each capsule represents one of London's 32 boroughs, highlighting how mathematics and design work together to create a modern engineering masterpiece. So this is our case's problem statement. The London Eye is a giant observation wheel that forms a perfect circle with a diameter of 135 meters and 32 equally spaced capsules around its circumference. Using geometry, we can explore the following problems. First, what is the total area of the circular wheel representing the total size of its structure? Second, determine the circumference of the wheel and use it to calculate the length of arc between two adjacent capsules. Third, if a capsule is cylindrical with a diameter of 4 meters and a height of 6 meters, estimate the surface area of the capsule in contact with the air as it rotates. So for our first problem, we were asked to find the total area of the circular wheel. So we were also given the diameter, which is 135 meters, and with that we can use it to find radius by dividing it by half, and we'll get 67.5 meters. And we do also know that the wheel is a circle, and the formula to find the area of a circle is pi r squared. So area equals to 3.142, which is our pi number, times 67.5 squared, which is our r squared. And we'll get our total area of the circular wheel, which is 14,315.7375 meters squared. And for our second problem, we were asked to determine the circumference of the wheel and find the length of arc between two adjacent capsules. So first and foremost, we need to find the circumference. So the formula to find the circumference is 2 pi r. So circumference equals 2 times 3.142, which is our pi number, times 67.5, which is our radius, and we'll get our circumference, which is 424.17 meters. And secondly, we need to find our angle between two adjacent capsules. So again, the wheel is a circle, and a full circle has a angle of 360 degrees. So and the wheel also has 32 equally spaced capsules. So in order to find the angle between two capsules, we need to divide 360 by 32, and we'll get 11.25 degrees. And last but not least, we need to find the length of arc between two adjacent capsules. So the formula is delta over 360 degrees times 2 pi r. So arc equals 11.25 degrees, which is our angle between two adjacent capsules, over 360 degrees times 2 times 3.142, which is our pi number, times 67.5, which is our radius. And we'll get our length of arc between two adjacent capsules, which is 13.2553 meters. And last but not least, our last problem, we were asked to find the surface area of the capsule if the capsule is cylindrical with a diameter of 4 meters and a height of 6 meters. So again, we were given the diameter, which is 4 meters, and with that we can find our radius by dividing it by half. So we'll get 2 meters, and we were also given the height, which is 6 meters. And the formula to find the surface area of a cylinder is 2 pi r h plus 2 pi r squared. So surface area equals 2 times 3.142, which is our pi number, times 2, which is our radius, times 6, which is our height, plus 2 times 3.142, which is our pi number, times 2 squared, which is our r squared, or radius squared. And we'll finally get our surface area of the capsule, which is 100.544 meters squared.
Slide similarities between a clock and the London Eye. First, circular shape. Both a clock and the London Eye are circular in a shape. The London Eye is a giant Ferris wheel and a clock has a round face. Second, rotation. Rotation is a both involved rotation. The hands of a clock rotation around its center, while the London Eye rotates to yearly passenger around its circumference. Third, center point. Center point is a boat have a center point that everything revolves around. The clock hand pivot at the center and the London Eye rotate around the central axis. 4. time awareness. Clock measure time and the London Eye move at a steady speed to complete a rotation in a fixed duration, giving a sense of timing passing. 5. The last one, visual structure. Boats often have spoke or division. A clock has marking or numbers radiating from the center like spokes, and the London Eye has spoke that connect the hub to the outer rim. So, let me explain to you what a difference between a clock and the London Eye. First, the clock have a small and light. But the London Eye have a very large and heavy. Second, a clock have a timekeeping, scheduling and precision measurement. The London Eye have a tourism, observation and structural engineering. Third, the size. A clock have a small size, but the London Eye have a humongous. Division. A clock have divided into 12 hours, but the London Eye divided into 32 capsules. The last one, function of rotation. A clock rotation is to show the time, and the London Eye provide panoramic views. That's all.
For the summary, we will talk about the uses of geometry in real life. First, the architectural marvel. Geometry serves as the backbone of architecture, guiding the design and construction of structures that define our landscape. From towering skyscrapers to intricate cathedrals, architects rely on geometric principles to create buildings that are not only aesthetically pleasing but also structurally sound. The second one, artistic expression. Artists too are indebted to geometry for the creation of visually appealing masterpieces, whether it's the symmetry in Renaissance painting or the uses of geometric pattern in Islamic art. Artists leverage geometric principles to evoke emotion and convey meaning through the work. The third one, everyday design. Walk into any modern home and you will find geometry at play in furniture, decor, and even the layout of room. Designers use geometric shapes to create functional and visually pleasing space, influencing our daily life without us even realizing it. The fourth one, navigation and mapping. Geometry has been crucial in the development of navigation system. Whether you are using a GPS device or a map, the calculation that helps you find your way are rooted in geometric principles. Understanding angles, distance and coordinates ensure accurate and efficient navigation. And last but not least, in conclusion, the example of the London Eye and wall clock show how geometry is used in real life to create both functional and aesthetically pleasing design. In the London Eye, the use of circle, triangle and symmetry ensures that the wheel is stable, balanced and safe, while the spacing of capsule is carefully calculated using angles and arc length. Similarly, in a wall clock, the circular phase and precise angles between hour and minutes mark allows for accurate and easy to read timekeeping. This example demonstrates that geometry is not just an abstract object, but a practical tool that helps engineers and designers solve real-world problems, create efficient structures, and understand the world through mathematical reasoning. That's all for today.